It's often necessary to reduce circuits to equivalent parallel circuits, EPC, or to equivalent series circuits, ESC. The equivalent series circuits would have an impedance equal to the reciprocal of its admittance. So if we take a look at the circuits illustrated below, we have a parallel circuit on the left, and we have its equivalent on the right. So we have converted a parallel network to a simple series circuit. So that's what we're going to be looking at in this section. So in doing so, again, we can rely on our expressions. In this case, we're going to take and solve for the polar impedance by using the polar admittance. Okay, so I know it's a little difficult to keep track of all of these terms. Y is admittance. So we are going to use the value of 384 at an angle of 37.9 degrees in microsiemens. That then, as a reciprocal, becomes 2.6 at an angle of minus 37.9. Okay, I hope you're getting used to seeing that this is really 1 over 384. So if I divide 384 microsiemens into 1, I get 2.6 kilo ohms. The angle then just changes the sign when we move it from the denominator to the numerator. So I hope you're seeing here now, as I promised you, you're building your tool chest here of the things that you need to do the analysis based on those first few chapters in the textbook. Those math principles are becoming very, very important now that you understand why we're doing them the way we do. So in this case, if we look at knowing the polar impedance, we can determine the values of R and the capacitive reactance, X sub C, that make up the impedance. So we're going to look at the left side here and the right side as our before and afters here. So Z polar then, as we said, was 1 over Y polar, that 384 at an angle of 37.9 degrees in microsiemens gave us that 2.6 kilo ohms at an angle of minus 37.9. Now I can use my definition of the cosine. Okay, in this case it's R divided by C. We manipulated our terms, so we're solving for R. 2.6 k ohms times the cosine of minus 37.9 gives us 2.05 k ohms. And you can see over here that becomes our series resistive value. Do the same thing for the capacitive reactance, Z sine theta now this time. And I hope you're understanding here why we're using cosine and sine the way we are. Cosine is the real component. Sine is the imaginary component. So when we run through the calculations, we end up with minus 1.6 k ohms. Okay? So you'll notice here 1.6 k ohms is not identified over here. They've identified the capacitor value, not the reactive value. So in our terms here, if we wanted to calculate the capacitive value, well, we have to run it through the expression for capacitive reactance, moving our terms around, and we get 199 nanofarads here. Okay, so here's our rectangular representation of our impedance, 2.05 k ohms minus J, 1.6 k ohms. Okay, again, find the equivalent series circuit and branch currents of the parallel circuit. So we've got this circuit that we see on the top as our before and the one below it as our after. Okay, so we've got a resistor at 12K, we've got a capacitor at 100 nanofarads, and an inductor at 20 microhenries. Okay, all of these relationships we've been through previously. They should not be a mystery to you now. We're looking at taking a parallel circuit, converting them using the reciprocal values that we learned for impedance and reactance. Now we're using conductance and susceptance. So we're calculating our susceptance both for the capacitor and the inductor. Everything then moves into Siemens. You'll notice then when we take these values, put them in the rectangular form, 83, 2.2 minus 2.2 gives us 83.3 minus 74. We can immediately put it into polar form. We get 112 at an angle of minus 41.8 microsiemens. Okay. To get the polar form of our impedance then, we take that value then and do the inverse. 112 at an angle of minus 41 gives us 8.94 at an angle of 41. Change the sign. To come up with each of our component values for R, X sub L, and L, we can take the definition, cosine theta is equal to R over Z, manipulate our terms, we get 6.67 k ohms of resistance. Well, you can see there it is right there. Okay. The next step then is calculating for X sub L. We get 5.96 k ohms, and solving for L, then we get 2.71 millihenries. So at this point, you might be asking yourself, what happened to the capacitor? Well, the capacitor gets absorbed into the inductor. Remember, we're dealing with a circuit that is either more inductive or more capacitive when we convert it. In this case, the circuit became more inductive. So we ended up with an inductor showing and the capacitor went away. So when we calculate then using basically Ohm's law for our voltage and each of our currents, we see that we have 8.94 volts, 7.45 microamps for the resistor. For the current in the capacitor, 19.7 milliamps, and for the current in the inductor, 20.3 milliamps. Let's go ahead and press on here with transforms, AC network transforms. These are methods shown previously that we might use to shorten the analysis by using something called a transform. Transforms allow us to equate series resistance and reactance to their parallel equivalent conductance and susceptance and vice versa. So if we want to convert from a series circuit to a parallel circuit, we use these forms where we have the conductance and the susceptance. Okay? If we want to convert from parallel to series, we use the resistance and the reactance. So let's look at an example. It's probably the easiest way to understand this. We have a parallel network over here. Our values are given to us in the reciprocals. G is equal to the conductance, 303 microsiemens, B sub C, 236. What we want to get to is on the right side here is the equivalent circuit. So in doing so, we solve for R by using these transforms. Okay, this is relationships where we're using pretty much just ratios of the value given by the sum of the values given. So in this case, the value given was G, the value given was B sub C. We're going to square them in the denominator, add them, and multiply them into the numerator. And so what we get on here as our solutions are our equivalent series components. Okay, so in doing so, we get 2.05 K, 1.6 K. You can see it here in the equivalent rectangular form where we just plug those values in. If we draw the circuit here, you'll notice that there were no inductors in this case, so we ended up with values of R and C. And in this case, if you want to know what the X sub C is, that's that minus 1.6. Okay, find the series conversion and the phase angle. First, convert the series to an RL circuit to its parallel. Okay, so we're going to take this parallel RL circuit and we're going to convert it to this series circuit. So we're using the relationships that we've already learned, X sub L, 2 pi FL, we end up with 6.28 k ohms. Now we can use these values in our relationships. G is equal to R over R squared plus X sub L. B sub L is equal to X sub L over R squared X sub L. So we plug our values in. We end up with a conductance of 2.53 microsiemens. In this case, we end up with 159 microsiemens. Okay, if you want to calculate then B sub C for the circuit, 2 pi FC, we multiply all of our terms together, we get 188 microsiemens. Take our values and put them into the admittance equation, G minus J B sub C. We sum all of our terms together. That's all these values up here. 2.53, 188, 159, and we end up with a simplified 2.53 microsiemens plus 29 microsiemens. Okay, now we're going to convert these into impedances and capacitive reactance. So we switch to the other forms that were given on the previous slide, and we end up with values of 2.92 k ohms. This becomes our series component now. Okay, and when we solve for X sub C, you can see that we end up with 33.8 k ohms. Okay, but in this case, I need the capacitor value because that's what we're driving to. If you look at the circuit, so if I take my relationship, X sub C is equal to 2 pi FC. That should have been, let's see if I can correct it. That should have been X sub C there, not C. I didn't convert it properly. So let's go ahead and fix that right here. We can do it. We can do it. X sub C. Okay, so now we've got it set up right. Because here our X sub C is down here at 33.8 because we're going to stick it into the relationship. And we get a capacitor value 470 picofarads. So that's our equivalent there. Okay, so now we have all of our relationships here for the new circuit. Okay, so we did some problem solving by doing some conversions here that allow us to convert one type of circuit to another.